Welcome to Tech Post. I'm your host, Trent Lapinski. In this episode, I interview Murray from D-Wave. They've just rolled out Leap 2, which is a new quantum computing solution. And in this episode, we talk about quantum computing and some of the use cases of quantum computing and how you can leverage Leap 2 to be able to work quantum computing solutions into your applications today. This is an amazing episode, so please stay tuned. Welcome to the podcast. I'm here with Murray from D-Wave. Tell us a bit about who you are and what you're working on.
Hi, my name is Murray Thom. I'm the Vice President of Software and Cloud Services at D-Wave, and I'm talking to you today because the team's been working really hard. We're launching a product at D-Wave Systems called Leap 2. It's got a whole set of new features to help users build quantum applications in production, and we think it's going to make it much easier for people to learn the technology and actually develop for their businesses and their mission.
And can you kind of summarize a little bit? I know quantum computing, there's a lot of components to it. It's a completely different method of computing. Can you kind of give a summary for the audience? Like, what are some of the major differences between classical computing and quantum computing?
Yeah, sure. So when you think about a classical computer, you're often thinking about like your laptop, but your phone is also a computer, and they have computer chips in them that can do calculations for us very quickly. The fundamental building blocks of what they're doing for us is arithmetic. They're doing addition and multiplication blazingly fast. But the world is nonetheless encountering a lot of complex problems that they're not able to solve with classical computers, despite the fact that classical computers are very powerful. And that's because there are a lot of problems that are just complex in a way where they don't break down into addition and multiplication efficiently. So a quantum computer is effectively taking a totally different approach. It's the fundamental building blocks of the chip are different. Instead of being classical, they're quantum mechanical. That allows them to do things that no other computers on the planet are capable of doing. And they accept a different form of problem. The quantum computers that D-Wave builds are tackling problems that are related to binary optimization. So when you need to optimize a problem in industry or in finance and material simulation or in machine learning, where you're having to make choices that are either happening or not happening, and those choices are related to one another. And in terms of your point about how quantum computers are different, I mean, they're accepting that different problem type, something that's complex for a classical computer to do. But then there's a lot about the physical systems themselves that are quite different. They operate at very low temperature, so they're running at 10 thousandths of a degree above absolute zero, which is quite exotic. And they're available in the cloud, which means they're easy to program from your laptop. And they also consume a very small amount of power. So, it's often very commonly known that classical computers are very power consumptive. In fact, it would not be uncommon, let's say, to use a rack of computers that would consume 100 kilowatts of power. The quantum computers that D-Wave Systems builds only consume 25 kilowatts, but the interesting thing about that is that the quantum computing chips themselves only consume a tenth of a billionth of a watt. So it's actually fascinating from a green technology point of view in terms of leveraging new technology to allow us to do calculations that haven't been accessible, but in a way that doesn't require that kind of energy consumption.
And you guys just rolled out a new solution called Leap 2, where you've now got access to a lot of these quantum computing resources now directly from the cloud. Can you talk a little bit about what you guys just rolled out, and you've got this new kind of hybrid solution? How does that work?
Sure. Well, the context for the announcement we have today is that 18 months ago, we launched Leap, which was built to allow hundreds of thousands of developers to be able to get their first real-time access to quantum computers in the cloud. But the thing we've learned from our users and our developers and our customers is that access isn't enough. So fast forward to Leap 2, we're releasing a nice set of features that should really significantly advance people's ability to build quantum applications in production and deploy them. One of the features, the first feature, is a hybrid solver that we've deployed in Leap itself. So it's a cloud-based hybrid solver. This is going to allow users to submit problems that are effectively 100 times larger than anything they've solved before. And it's going to return high quality solutions to them by deploying that problem across a workflow of both classical computers and our quantum computers in the cloud, and then coordinate all that, handle all the parameter tuning, and return the answer back. The second really interesting feature that we think people will be excited to use is that we've incorporated a comprehensive integrated developer environment, an IDE, into Leap itself. And that is going to allow people and developers to entirely build their quantum applications directly in Leap. It simplifies the entry point to getting started, becomes pre-configured with tools and its ability to program the quantum computer. And we've also released a searchable collection of examples to help those developers get started. And thirdly, we've released a visual problem inspector. And this is going to allow users to see the relationships between the problems that they're solving and how they get translated into quantum machine instructions. As well, they'll be able to interpret those relationships with visuals that show them the quality of the results they're getting back, as well as warnings and tips for how to improve their programs. So it's really going to allow users to get much more advanced, to understand the technology more deeply, and to learn how to performance tune their programs more effectively.
And some of the examples that in the presentation that I saw from you guys earlier, can you talk a little bit about some of those examples? So like, what are the use cases? So if someone's listening to this who, is kind of new to quantum computing, doesn't completely understand how it works, what are some of the real world problems that you can now solve with quantum computing, with these algorithms, with these solutions, and then being able to build those into the applications we're using in the cloud and on a daily basis? What are some of those use cases? Like, for example, you had one that was like social networks, looking at terrorist networks, gangs. Like, how can you use quantum computing to kind of break these things down and create useful data sets?
Yeah, that's a great question, Trent. The place I'd probably start is that in 2019, we had our first example production application that was run in the cloud by Volkswagen. So at the Web Summit in Lisbon, they actually were optimizing the shuttle buses for the conference using the quantum computer and some of the applications around. So they had phones for each of the drivers that gave them a route map that were done with partners that helped them create that navigation. That was basically coordinating with a central system which was looking at traffic flow across Lisbon generally. And then it was making calls to the quantum computer in the cloud to optimize which routes those buses should be taking, and then sending that information back to the bus drivers. There was a driver who had 20 years of driving experience who commented that the map suggested a different route for him than he would have otherwise taken, and he was pleasantly surprised to find that it was faster. So that's probably, I think, one of the most tangible examples where a problem we're all familiar with, trying to get mobility in a congested area, right? Traffic flow in a city, that can actually incorporate quantum computers, and that's a quantum application. And that, I think, is an important example to reflect on, because all quantum applications, every quantum application in the future will be hybrid and always will be. And the reason is because effectively, you can't even run, construct, calibrate, or interact with a quantum computer without our laptops and our Python programs and the internet and the cloud. The degree to which it's hybridized and how you're using the quantum computer in that hybridization will change from application to application. So that's one example. Another example is a company that we've been working with is Menton AI. Menton is doing protein synthesis and design. So they're trying to design proteins that have exhibit particular behaviors. And we've been working with them to develop a hybrid technique for them to be able to do that design that produces better predictions of what the protein's behavior will be once it's synthesized. And the exciting news is that the first quantum design peptide has been synthesized and tested for its properties. So those are two examples. Some of the other examples we looked at are analyzing social networks. There's a group of researchers at Los Alamos National Laboratories who studied publicly available data sets showing the social interactions amongst terrorist networks in the world. And they studied a form of analysis called structural imbalance, which is computationally very challenging for a classical computer to do, that actually maps very natively to the quantum computer. And it allows them to ask the question of, in this social network, is it possible to separate two groups so that within the groups there are only friendly relationships, and between the groups there are only hostile relationships? And that's a form of binary optimization in the sense of, which group is it going to be in? Is it going to be in group blue? Is it going to be in group yellow? And what kind of a relationship do they have? Do they have a friendly relationship, or do they have an antagonistic relationship? The reason that's particularly interesting is because the research has shown that although that analysis is complex to do, it's predictive. It can be shown to be predictive of violence. And that's the kind of analysis that these researchers are really excited about is, rather than reacting to violent events, let's try to be able to study social interactions to anticipate them and maybe take diplomatic means of diffusing situations before they escalate. Those are sort of three examples of practical applications, and there's many more. Physical networks, communication networks. We've talked to companies in Japan who are doing web advertising. They're optimizing the movements of automated guided vehicles in factories. So really, the world of possibilities is open. We've tried to create the open source tools and the examples to help people get started, but we're expecting to learn 100 times more from our developers than what we've tried to do in the past as they get a handle on these new tools and put them to use.
Is there any use case in particular that's been really fascinating to you personally? Is there something that maybe you didn't think about before that you could use quantum computing for, or something that, maybe one of the developers has tried recently that you didn't think about as a possibility?
I think there's so many examples of that. I think that as I've talked to people who are doing work in healthcare and pattern recognition for personalized medicine, that's a very exciting field. There's a lot more information we have today about the experiences that people have. I guess the way I would characterize it is that, medicine today, or where it was 20 years ago, was based on the notion that any treatment which worked for everybody was medicine, and any treatment that didn't work for everybody was just tea. And what we're learning now is that people have lots of differences in their bodies, in their metabolic gene expression, in their gene sequencing, in their RNA. So how can we use those patterns of information to try to predict people's positive or negative reaction to treatment? And I love the idea. I'm fascinated by the idea that, as a technologist, I was building this technology to try to put it in the hands of users. And someday people might be able to detect patterns so that they can better determine if someone's going to respond well to treatment, save them the trouble of taking treatments that aren't effective for them, and maybe even identify groups that are underserved by treatment programs we have right now, and use that ability to anticipate that to develop new treatments for them. So I'd love to be able to impact human health in a positive way using these kinds of pattern recognition tools and optimization tools.
Yeah, and there's definitely something to that, because different ethnicities, different population groups, even just the difference between genders, that all of these different things can be factors in how someone responds to a medication, how they respond to a certain treatment. You've got cases where you could do predictive analysis and figure out who's going to be susceptible to cancers or future health problems, and then you could put interventions in place, or actually cures in place in many situations. And if you've got the data to be able to do that and analyze that, especially in real time, that's we're entering a new age here to be able to do stuff like that. So I definitely see the benefit of having these, essentially APIs and these toolkits to be able to get these, this technology into the hands of developers, because, for the most part, previous to this, you've kind of had to work for a major tech company to get access to quantum computing. You had to be in a certain lab at Google or, one of these major tech companies, where now D-Wave, it seems like you guys are making this technology accessible to pretty much anyone.
It's such an interesting story, Trent, because it's true inside D-Wave and it'll be true in the industry more broadly. Part of the reason why D-Wave has been as successful as it has is that it's not just quantum physicists who work at D-Wave. We've got electrical engineers, we've got mathematicians, we've got statisticians, and it's when you bring a diverse group of people together to come together to solve a problem, that's when you get some of the most innovative solutions. That's been something I've observed in the, almost 18 years I've been working at D-Wave. And we're taking that same model in terms of how do we engage with the community. There's been a lot of effort in building quantum computers now, but the really exciting opportunities are in using quantum computers and building the software and the applications. And that's why we've also created a help center with a community, a set of community forums, so that developers who are programming the system can also interact with people who have domain expertise. And my hope would be that if doctors or researchers in health science are interested in how quantum computing could impact it, they might go to that community and then put a post up and saying, hey, who knows how to do this kind of pattern recognition for this data set? And that other developers would be like, oh, that's an exciting problem. Let me see if I can write an example, load some of the searchable examples and modify them to handle that data set. That would be a huge, just an exciting opportunity in my career in terms of seeing that come together, because I certainly don't have that domain expertise, right? We need to be able to create those sharing opportunities for that magic to happen.
And it looks like you're using a lot of open source tools as well. So a lot of these innovations are going to potentially get kicked back to the community.
Yeah, absolutely. We're totally committed to open source. I mean, the nice thing about open source tools is that they're easy to get in people's hands. I've worked with a lot of organizations that need to have a lot of approvals for software, and if it's pre-compiled, that creates a lot of challenges. But also, just in terms of getting in the hands of community members, I've met 8-year-olds who are programming our quantum computers because we have open source tools. And the other important aspect of them being open source is that although they do functions for you, if you want to learn how those functions are working, you need to be able to see the code itself. And it's really important that we provide interfaces for this technology and the applications, and the products that people can come in at their level. So if they have a lot of expertise in quantum algorithms, they can come in at a low level. If they have a lot of domain application expertise, they can come in at that higher, more abstract level. And, as that community comes together and starts interacting, they're actually going to find those partners, the people they would work with who will help them tune performance or map it to the actual problem and become more effective that way. So, there's so many more smart people outside of D-Wave than we have at D-Wave. And I'm very proud to work with all the colleagues I have here. I think that we've seen a huge acceleration, in the context for this is that we launched Leap 18 months ago. At that time, people were getting their first real-time access. We had 80 early applications that were developed for the system. In the next 18 months, that's grown to 200. And we've been commercializing quantum computers for 10 years. That means in the last 18 months, we've more than doubled the number of early applications than in the previous 9 years. I think that's exactly what we're going to see, that acceleration with Leap 2, because the systems are so much easier to use. We're lowering the barriers to use. We're providing the environments right in Leap for people to be able to program. And we're creating these visual tools, so that people don't have to discover information. It's kind of brought to them.
And how do you think bringing this technology is going to have an impact on automation and a more automated future?
Yeah, that's a great question. I mean, there are some fascinating connections between how the quantum computer is working and machine learning. So the quantum computer is effectively like a network of things that they make binary choices. They turn on, they turn off, and they interact with one another when they do that. So if one turns on, it either tries to turn this one on as well or to suppress it. That's actually very much like a neural network model. In fact, our brains have neurons that fire or they don't fire, and they have synapses connecting them to other neurons that either get suppressed or excited. And that's a lot of what the machine learning community has used as inspiration for a lot of their algorithms. So they're basically proposing mathematical models that are like neural networks, and then they try to train their connections through exposure to data so that they start to exhibit patterns that kind of correlate with when the occurrence of the data is. So that's actually, there's a direct connection between a machine learning model and what the quantum computer does. I actually find it really easy to explain to those practitioners because I can say our quantum computer samples from a sparse restricted Boltzmann machine For my family, that statement doesn't mean anything. But for people in machine learning, they're like, oh, I know how to do that, right? I do that all the time. So there's been some fascinating research papers and results put out in terms of incorporating the models that our quantum computer can resolve into machine learning techniques. It's very early work, and there's lots of progress there, but there's a lot of synergy between the capabilities of the technology and the needs of those approaches.
Awesome. And do you have any final thoughts before we wrap up?
Well, yeah, I think that, just touching on kind of what we talked about, we've been listening to our customers, and they've been basically telling us one of the most key challenges to them building quantum applications in production is, the problem sizes they can fit directly on the processor. So I'm really excited about this hybrid solver service. I think people, when they interact with it, are going to find it a much lower barrier. I'm excited to see what they do with it. We're hoping to see this response, and that people actually get an opportunity to see what resources are available to them in the service so they can start building quantum applications right away and use those features like the problem inspector to see those connections. Probably the last thing I would mention is that, later this year, we're planning to launch our next generation quantum computing technology called Advantage. It's going to have more than twice as many qubits. It's going to have many more connections. It's going to have 5,000 qubits and about 40,000 couplers in it. Any users who are using this Leap 2 system that we have now are going to find that their quantum applications just seamlessly port over onto that new technology. It's all been designed with that in mind, so that users don't have to pick the right time to use quantum technology. They can basically get started right away. They've got the algorithms and the quantum computers and the hybrid algorithms. The more applicable the technology gets, or the better the hybrid algorithms get, the more their application gets accelerated. And they don't have to worry about, trying to time things or learn too much about, predicting the future. So let's see how it turns out. I'm really excited to see people get on the system, and it's been great talking to people about it and talking with you today, Trent.
That's a really exciting point that you just made there. I mean, I'd never really thought about that before, but as hardware improves, you don't necessarily have to refactor all your software because it's just going to actually start running more efficiently, which is a major difference that we've had with classical computing where, when you're moving between bits, you often have to rewrite your software. So that's pretty cool that as we get better hardware, we're not going to have to rewrite our software. That's a major advantage. So anyways, it's been a pleasure having you on. This is some fascinating technology, and thank you for explaining it to me and our audience.
Thank you, Trent. Talk to you soon.
Take care. Thanks for watching another uncensored episode of TechPost.io. I'm your host, Trent Lapinski, and don't forget to subscribe to us on YouTube and hit that little notification bell next to the subscribe button so that you can get notified when we release a new episode. You can also find us on iTunes, Google Play, and other social networks, including Twitter and Facebook, at TechPost.io, and you can find me personally at Trent Lapinski. Once again, I'm Trent Lapinski, and this has been another great episode of TechPost.io. We'll see you soon.